Is that working for you? Can you? Okay, very good. So, okay. So I thought I'll discuss a little bit about star formation, and then with a particular focus on in this first talk on the stellar mass distribution, because this is a very important quantity in astrophysics. The distribution of stellar masses impacts almost everything in astronomy, from from the stellar clusters where stars form, depending on if we have more or less massive stars, the cluster evolution will be different. It impacts galaxies and the way they evolve, both dynamically and chemically, because massive stars inject heavy elements in the interstellar medium when they die out. And so if we have more massive, in abundance of massive stars, we have a fast chemical enrichment and so on. So this is a very important quantity. And then the terminology is important. So I will start a little bit by defining what is the IMF, or the initial stellar mass function, and giving a little bit of a historical background, how people started to find results about this. So the program is more or less about this, but I probably won't be able to cover everything. So the definition of the IMF, then I'll discuss some measurements of the IMF, particularly on the scale of clusters, individual star-forming regions. And then the IMF in the Milky Way as a whole, in the galaxy. I will skip the part on external galaxies. This is very interesting, but it would take some 1 or 2 lectures on its own. But then I'll try to cover a little bit about the origin of the IMF from the perspective of theory and numerical simulations. So different ideas about how stellar masses come about. So what is the IMF? The initial stellar mass function. So initial stands for, when a single generation of stars is formed. I think Priya probably has discussed this at some point in one of her lectures. It's the, in a star forming region, you have a stellar population and you have a certain stellar mass distribution which will come out. So in terms of notation, you can find in the literature 2 notation. One is, let me see if I can put the cursor. Yes. Sorry. You can find the notation in the distribution of stellar masses written in the form of dndm, which is the number of stars in a given mass bin between m and m plus dm, or it can be in logarithmic form. So it's dn d log m. So it's the number of stars which have masses between log m and log m plus dn log m. And there is a direct correspondence between them, which is given here. And then if dn dm, the linear mass function is a power law, then dn d log m is also a power law, and there is a correspondence between the exponents. The exponents of the dn d log m is the exponent of the dn m minus 1. So in young clusters, young means somewhere around a few million years before the gas has been expelled from the cluster, and most importantly, before a lot of dynamical evolution has occurred. So in those clusters, the young clusters, if we observe them, we observe always a present day mass function. But to first order, this is going to be very close to the IMF. But in evolved clusters, say that are a few 100 million years old or even more, giga years old, the present day mass function isn't the IMF. It can be affected by many things: dynamical evolution, which leads to to an evaporation, dynamical evaporation of the clusters, and to the effects, for example, of stellar evolution at the high mass end. So many massive stars would have disappeared or would have lost much of their mass. so in galaxies, many people talk about an IMF, but it's a little bit of a stretch, a big stretch, because the IMF of galaxies is you can, if you have an ensemble of clusters forming within a time lag of a few million years, and you sum all those clusters together, you can talk about a galactic IMF or a galaxy-wide IMF. But if you are looking at the present day mass function of the galaxy, it's very hard to call it an IMF, because it has to be convolved. The IMF of each episode of star formation every, let's say 10 million years has to be convolved with the star formation history of the galaxy. And the star formation history is not only the secular evolution, that you have more massive clusters forming at redshift equal 2, which affects the shape of the IMF at that epoch versus the shape of the global IMF at the present redshift, but it's also, you have to account for the star formation history in terms of all the minor mergers the galaxy undergoes, and this affects the present day mass function as we see it today for a given galaxy. So it's a little bit of a stretch to call the mass function of a galaxy in IMF, but it's often done in the literature. Let me see. Oops. Right. So I'm seeing some problems with the cursor here. Let me see. I'm going to, I'm not seeing much of the text on the top. So anyway, this is just summarizing what I was saying, that in galaxies for stars which have, so this is a first approximation. I mean, this is not the real thing, but it's to first order for stars who have a main sequence smaller than the age of the galaxy, you have to correct for the effects of the star formation rates. So this is what's shown in the bottom term here. And on top, if the reverse is true, if the main sequence age is larger than the age of the galaxy, and this is under the assumption that all the stellar mass function in every individual cluster is the same as the one are similar, then you can sum them up, and the present day mass function will be similar to the IMF. Okay, let's discuss what have been found for the galactic field. So one of the first and popular works, I mean, it's not actually the first person to have looked at the IMF of stars, but his work has been a little bit more comprehensive. So this work was done by Edwin Salpeter in 1955. So what he did is look at stars in the field of the galaxy within a relatively small distance. I don't remember the value, but maybe 20 parsec or so. And then he calculated the luminosity function. And then after some steps, which I will hopefully describe in the next slide, you can go from a luminosity function of stars to a mass function. And then he described this mass function, dndm, as a power law. And so m to the power minus alpha, or dnd log m to the power minus capital gamma here. And he found that alpha is equal to 2.35, and equivalently, as I said before, gamma is alpha minus 1, so 1.35. So on the left, you see the luminosity function of stars derived by Salpeter. So this is the magnitude, the visual magnitude, absolute visual magnitude, and this is the derived on the right, the mass function. You can already see that it's not exactly super, a very neat power law, but to first order it is, and so so that's what he found. And then, so this is a present day mass function, right? I mean, this is a present day mass function. So the way you want to go from the luminosity function to a stellar mass function is that you want to know the luminosity function. You want to know the scale height, the galactic scale height for a given visual magnitude, and you want to know the fraction of stars within a visual magnitude. So this is a work, I like this paper by Miller and Scalo because they detail all these steps very nicely. So you have a certain luminosity function. And then you have a scale height of the magnitude as a function. So the magnitude is function of scale height. So the bright stars are located at low heights, so in the disk basically, and then you have dimmer stars located at higher galactic latitudes. So you have the mass luminosity relation, and then you have the fraction of main sequence stars as a function of luminosity. So this is the mass function that Miller and Scalo derived. So it's basically this roughly the same work as Salpeter, but they looked at a larger volume. And so interestingly, so this is one of the first steps where people started to see a turnover at low masses. So Salpeter had a single power law, and then now we see some kind of turnover at a fraction of solar masses, at say maybe a 0.3 or 0.4 or 0.25, depending on your model. And so, of course, as I said, you have to convolve with the star formation history. So this is in the case of a constant star formation history. This is what I just said before. So the stellar mass function is the same as the present day mass function for stars whose main sequence lifetime is larger than the age of the galaxy. Otherwise, you have to multiply by this corrective factor. But you don't have to assume a constant star formation history or star formation rate. So this is we're talking here about the volume in which Miller and Scalo have looked. This is not the constant star formation rate necessarily for the entire galaxy. So just for the local volume in which they determine this luminosity function, you can assume what they call maximum a decreasing birth rate or an increasing birth rate or a constant birth rate, which is this one. And so you get some variation in the resulting IMF. But by far and large, it turns out to be a power law at the high mass end and with some turnover towards the low mass end. So Miller and Scalo have been a little bit, I think, more open than others, maybe more open than us today. So they tried to fit this function with different functional forms. So, for example, a polynomial in log m, log normal distribution, here with a certain width and characteristic mass, and a multi-component power law. So a broken power law as a function of different mass ranges. One critical point in all these mass determinations is the knowledge of the mass luminosity relation, because I think I'm just going to come back a few slides. I should have stressed this point here that the mass function is very sensitive to the dm d log m, so the slope of the mass luminosity relation here. So you see dmv d log m. So if you have an incomplete knowledge of the slope, or because it can get very steep, then you make big error in the mass determinations. So this relies, of course, on basically stellar evolution modeling, and you know that stars of different masses evolve differently, and radiation, for example, in high mass stars become very important. So one has to derive the most accurate possible mass luminosity relation. There are many different stellar evolutionary models. For example, the most popular ones in the low mass regime are the ones by Isabelle Baraf. But it's not the only ones. But so for high mass stars, there are models by Lionel Sies, Menet, and Meder in Geneva, and then there are also many other models in the Bologna tracks and so on and so forth. So all this is very important to know in the background, that actually in mass determination, you don't determine masses directly of stars. We always determine luminosities, and then we have to convert into masses. Okay. So some more recent determination of the galactic field, so the field of the galaxy. So we're not looking at adding particular clusters. These are the stars that are distributed in the galaxy. There is a determination by Paravano, Maki, and Hollenbach. Actually, this should be 2011. So it is using more recent data from the local volume. And so they, so what the function they found, I will describe the mathematical function a bit later, is this phi STPL tapered power law, single tapered power law function, and then they compare it to the salpeter, to the Krupa, Chabrier, etc. And then there is a determination by Bochansky et al. In 2010 for the low mass components of the galactic field. It looks a little bit power lowish, log normalish here. So and then if you can, in both cases, what you derive always is a system mass function. So it means it's uncorrected for binarity. But then you have to make some assumptions to derive the single star mass function, and you have to introduce some binary corrections, which are based on what we know empirically from the galactic field, because we have some higher resolution observations for binary systems. So we know which stars, what is the binary fraction of stars of different masses. And for those that are binary, what is the mass ratio between the primary and the secondary star. And so, and you can also rely on numerical simulations, but with all the incompleteness that characterizes the simulations. And then you can correct from system IMF to single star IMF. So nowadays, there are many functional forms of the IMF or of the stellar mass function that are in circulations. Depending on which paper you read, you will find that people use different formulations. So you have a multi-component power law. This is popularized by Pavel Krupa, 2001, 2002. So it is basically the mass function is m to the power something, and this something depends on the stellar mass range that you are looking at. So you have a mass range for brown dwarfs, and then for low mass stars, intermediate mass stars, and high mass stars. I should probably say something that Krupa, his work is not a direct determination of the mass function of the field, of the galactic field. So Krupa never looked at the entire galactic field and derived the mass function or re-derived the mass function from the field. What he did is different. He looked at many clusters and plotted these alphas of clusters in different mass ranges. For example, let's say alpha 0 or alpha 1. He plotted this alpha 1 for many clusters, and he calculated the mean value of this alpha 1 for this particular mass range, for example, 0.08 to 0.5 for alpha 1. And alpha 1 here is the mean value. And the errors, there are errors, is this, the 1 sigma of this population of clusters in that mass regime. But it's not a direct determination of the field. Then there is the log normal distribution by Chabrier, and so his determination is based on this Reed et al. Data. So he proposed a log normal, so it's a log normal distribution for stars below 1 solar mass, and then it's a power law similar to salpeter above 1 solar mass. So it has this dichotomy and this breakpoint at 1 solar mass. Fundamentally, in my opinion, there is nothing special about the 1 solar mass, except that it's a convenient way to connect the two mass functions. Then there is the tapered power law, single power law, tapered power law IMF, which has been used by different people. And it's given here in the bottom. So it has a slope at the low mass end, the little gamma, a slope at the high mass end, the capital gamma, and it has a characteristic mass which marks the position of the peak. And so for the galactic field, if you fit the distribution of stellar masses of the galactic field with this function, you get that the low gamma is 0.57, the upper gamma is 1.35, so actually they didn't really fit it. Barafano et al., they adopted again saltpeter value, and the characteristic mass is 0.42 for the system IMF, or for the system mass function, and around 0.35 for the single star IMF. And so this gives, in the upper, the plot gives you a comparison of the different mass function scaled for the same reservoir of mass, and you see that things differ between the different mass function. For example, actually already between the Chabrier and the saltpeter, there is a factor 2 in the high mass stars, because saltpeter is a single power law, and Chabrier, albeit it has the same slope, but it has a turnover, so there is a shift by a factor of by a certain factor of 2. You see between the total number of stars in that mass regime, depending on which form you adopt. Okay, these things are still very much in circulation, but there are more interesting work, I think, now coming. And I say more interesting because these determinations were either based on clusters like Krupa, or like Chabrier. For example, Chabrier had to make the assumption of a constant star formation rate for the galaxy. But we know this is not true. We already suspected this is not true, but we actually have the confirmation now. So there is a very nice work, I think, by Roger Moore in 2019. So what Roger did, he's used the hierarchical Bayesian inference model to infer simultaneously the time average IMF and the star formation history of the galaxy. So without going, because the paper is very technical and mathematical, but without going into that detail. So what he does in simple words is that he compares a model, which is the Bezanson galaxy evolution model, which gives you an idea or constraints on the structure of the galaxy, the potential of the different components of the galaxy, and hence also their dynamics of the stellar component. And it gives you constraint about also the chemical evolution of the galaxy. So the metallicity at different locations of the galaxy. And so he tried to match that model with observations of both the structure and dynamics coming from the Gaia satellite and from the chemistry of stars, from the chemical composition of stars from the Apogee catalog. By doing this simultaneous inference, of course, there are more parameters than the shape of the IMF and the star formation history of the galaxy. There are parameters such as the scale heights of the different components of the galaxy, the thick disk, the thin disk, etc., the radial scale length, and so on. So you have to, this is why you need Bayesian inference, because the parameter space is very large. You cannot just by minimization of a certain chi-square compare models to galaxy, to data in that case. But in conclusion, what they found is this, what I'm showing, the result on the top figure is the inferred star formation history of the galaxy. So as a function of age, age equals 0 means now, and age looking back in time. And you can see that, so the models here, G12 and P, are all models. All of them are models. The G12X S is a different model, is a model where you actually impose the shape of the star formation history to being a decaying exponential. So if you impose this constraint, the shape of the star formation history, you get a star formation history which is like this, in the blue points. But if you leave it as a free parameter, you leave the shape of the star formation history as a free parameter. So basically what that means is that for every bin at a given giga year, you have a free parameters that tells you what is the star formation history. So actually you are inferring all these different points in a free way. Then you get a star formation history which shows a bump here at about 3 giga year. And this means that this can only mean, so it is a decaying exponential. You can see that at 10 gigayears it's up and then it decays, but then it has this bump at 3 gigayears. And this 3 gigayears is likely to be a minor merger the galaxy has, our Milky Way has undergone, which could not be spotted if you impose the shape of the star formation history. And then he inferred the shape of the IMF of the galaxy. In that case, he didn't take a different IMF for every gigayear. He took a single IMF, which represent a certain time average for the Milky Way. And these are the slopes. So here on the bottom figure, he shows the slope as a function of stellar mass range. You can see, so his models are the ones that are in within 1 sigma in orange. So above, let's say, a solar, solar mass or 2 solar masses, the slope is similar to the predictions of the Krupa and so on, so Peter, maybe a little bit shallower, around 2, whereas the others is 2.35, if you remember. In the intermediate mass regime, which is around the peak, we have a slope that is close to 1.35. So this is okay. It compares very well to the other prediction. In the low mass regime, you can see that he finds a slope that is within 1 sigma. Maybe the mid value is around minus 0.2, and the models, for example, of Krupa is way above. If you remember, 1.35. The Salpeter, because it's a single power law, it's 2.35, and so on. So the models are much higher. We were very pleased with that. Together with Shantanu Basu, we published a model for the IMF in 2018. And so this, our line here, the dashed line, is just at the tip of the inference done by Moore et al., and it's 0.5. So it's not so off from what they found from the observations. So this is one example of a recent determination of the IMF of the galaxy, although it's a time averaged IMF, so it's not very fine in time, because doing an IMF that is very fine in time would require adding many more parameters. There have been many similar studies by Rybicki and Just in 2015, also by Moore, Solima in 2019. However, all these studies here assumed a decaying exponential for the star formation history. And as a consequence of that, because you impose the shape of the star formation history, this affects the shape of the resulting IMF. And these models find a slope that is very steep in the high mass range of around 3. For example, if you look at the bottom plot, you can see that the predictions of, or the inference of Rybicki and Just in 2015 gives you a slope which is close to 3, much higher than any other inference, and not really constrained by any other observations. So in inferring the mass function of the galaxy, one has to allow for a certain freedom for the star formation history of the galaxy to be taken into account. So I'll move now from the galaxy as a whole to single clusters. The idea here is to say, well, so you saw that the stellar mass function of the galaxy, whether the present day mass function or the IMF of the galaxy, is still work in process. So we still don't have the full answer or the full conclusion about this, although we are getting more and more interesting results. So the question is whether the IMF of clusters resemble individually the stellar mass function of the galaxy, or whether they differ from it, and if so, by how much. So before describing results of individual clusters or population of clusters, I want to stress a point here is that statistics is very important, meaning that we really need to, before making a statement of whether the IMF is universal or not universal, we should worry about the number of clusters we are looking at. And why is that so? Because if we assume that all the stars that form in the galaxy in a given period of 10 million years are formed in clusters, and if we assume a certain shape of the cluster mass function, the distribution of cluster masses now, let's say this distribution is a power law, dn over d mass of the cluster is proportional to mass of the cluster to the power beta. And this beta, for example, is -2. And let's assume a star formation history of the galaxy, which is anywhere between, I'd say, 0.5 to 1.5, which is about our current knowledge of the star formation rate in the galaxy as a whole. If we combine this information together and we take certain cutoffs for the low mass cluster and high mass clusters of, let's say, 50,000 solar masses for the most massive cluster and 50 solar masses for the low mass clusters, we will get that the galaxy will be forming several 10,000s of clusters, and maybe even 150,000 clusters or more, actually, depending on these different parameters. So the galaxy is forming per cycle of 10 million years, is forming anywhere between a few tenths of thousands to a couple of 100,000 clusters. So if someone comes and tells you, I have 2 clusters which are identical, therefore the IMF is universal, you should be very wary, because a sample of 2 is basically equal to 0 in statistical terms. So some people, of course, compiled some clusters and compared them together. So this is a plot taken from the review by Bastian et al. In 2010. So the plot shows here on the left side younger clusters, so associations. So these are young clusters, and then going down to open clusters that are a bit older on the right side, maybe 100 to 400 million years, like the Pleiades and the Hyades, and then also showing global clusters, which are old systems. And this is shown, all of them are compared to the galactic field, which is shown here in the at the bottom with the yellow triangles. So the conclusions of Bastian et al. Was that the IMF is universal. Personally, I disagree with this statement, but it's actually a matter of, as I said, it's a matter of statistics. You have to have enough statistics to make this conclusion. And then you can see that the IMFs don't exactly look exactly the same. I should also point out that for the young clusters that are shown here, the most massive one is the ONC, Orion Nebula Cluster, and all the others ones are low mass clusters, like IC348, Taurus, Rho Fucus are all low mass clusters. So I added my grain of salt to this controversy by publishing a paper in 2014. In this paper, I took 8 younger clusters. So why young? Because we want to minimize the effects of dynamical evolution, make sure that most of the stellar population at the time stars form is still within the star forming regions. And so what I did was also a model based on Bayesian inference. So basically you have the stellar masses, and instead of putting them in a bin and then fitting the mass function with a certain functional forms, what you do is you try to minimize, to walk into the parameter space. And the parameter space is 3-dimensional. It has the capital gamma for the slope at the high mass end, the small gamma for the slope at the low mass end, and the characteristic mass. I show it to you here. So here is the high mass end, the low mass end, and the characteristic mass. So this is the plot on the figure on the right. And so the idea is to infer these 3 parameters, small gamma, capital gamma, and MCH, for these 8 young clusters and compare them to each other and compare them to the field. So the cross here, there is a cross in each figure, which it shows the value of the field. So for the small gamma is 0.57, the capital gamma for the galactic field for the galaxy as a whole is 1.35, and so on. And so the plots here in the bottom panels show you the probability distribution from the Bayesian inference for the for each parameter for each of these clusters. So the idea is very simple: is that if those clusters are very similar to each other, we should have a global overlap between those 1 sigma contours, for example, and they should also overlap within the galactic field. What we see is that there is some kind of in the parameter space, the most likely value of this 3 parameters for this ensemble of cluster do not have a global overlap, at least within the 1 sigma confidence interval. And so this is probably indicative of some level of variation already. But you can argue, of course, that the sample is small, and this is true. The sample is indeed small, so it's 8 clusters. Remember, I told you the galaxy is forming 10,000 clusters or more per cycle of 10 million years. So we have an example here of 8 clusters only. So that's a very good point. It's not enough, but it's already indicative that actually maybe they are not exactly all the same. I should say, to be fair on the other side, is that the stellar census of this clusters is constantly evolving. So these the stellar census of these clusters were done using data before the Gaia era. So there was an assessment of cluster membership using proper motions and so on and so forth. But everything probably has to be redone and reevaluated. Also, I limited the sample to 8 clusters because these had stellar masses for whom the masses were derived using the same evolutionary tracks, which is important because otherwise you introduce a different additional level of bias in the comparison. So to try to improve the statistics, we looked at a different method. And again, it will be a little bit too much to go into the details of the method in its entirety, but I want to just give you an idea of the conclusions here, what we found. So assume we have a stellar population, a population of clusters, and then in the galaxy, let's say 10,000 clusters, and then we take that all these clusters have the same IMF, the same functional form, the same parameters. They have the same IMF. Of course, what varies between cluster to cluster is the masses of the clusters, because we have low mass clusters, high mass clusters. So the shape is the same, but then just what varies is the normalization. If we take this population, we can measure any quantity that we want. What we measured is the fraction of isolated O stars, massive stars in those clusters. But what I mean by isolated or single O stars is that it's the fraction of O stars that are unique in their cluster. So this is a cluster which have only one O star above 15 solar mass. And so we measure the fraction of single O stars, means that we measure the number of O stars that are single divided by the total number of O stars. And what we find is this this value here if you look at the orange points towards the right, you see, I don't know if you see the cursor, but you can see that you have the model called FDP sigma ops. You have an orange point, right? Is that so? Sorry. Look at sorry, not at the right, at the left, completely at the left. You have this orange point, and the fraction here is around maybe 18%. We measured the same fraction for an observational sample of clusters, this fraction of single O stars, and we found this dashed line. So the fraction is around 13%. So within the 1 sigma, if the IMF of all clusters is the same, it doesn't match the observation. Now what we did is we took the same clusters, and instead of giving them the same IMF, we started giving them parameters of the IMF, which were drawn from different distribution function with a different shape. So for example, the capital sigma here, the capital sigma, the capital gamma and the small gamma and the MCH were assigned Gaussian function of a certain width. And we played with the width of these Gaussians. And for each family of clusters, we measured the fraction of single O stars. And again, we compared it to the observations. And as you are going from the left to the right, you are increasing the scatter in this distribution, the width of this parameter distribution. It means that the models on the right have more variations in their IMF than the models on the left. And we show that in order to fit the observations of single O stars, we need to have a population of clusters for which the IMF varies. And how much variation do we need? For example, we show that we need about a standard deviation of the high mass slope of 0.6 around the salpeter value. Remember, the salpeter value is 2.35. And so what we show is that we need a scatter of 0.6 around 2.35. So we will have within 1 sigma clusters that can have a slope of 3 and other ones that can have a slope of, let's say, 1.7. So this is a test on the variability of the IMF. I said we used this method to increase the statistics. The observational value here, the dashed line, was obtained from the statistics of about 350 clusters, which is not 10,000, but it's better than 8 or 10. So it improved a little bit the statistics of the inference. There are many other cases of or evidence of against universality. So here I'm showing you in the left plot a derivation of gamma, so the slope at the high mass end of the IMF plotted as a function of surface density. So this is a combination of data from Daniel Weiss for M31 Andromeda galaxy, and by Bomdolim for galactic clusters from the Milky Way. There might be a dependence on the surface density of stars, but what is important now is to see that this capital gamma varies between 0.4 to 2.5. The salpeter value, I remind you in this notation, is 1.35, the capital gamma, 1.35, which is around here. So just shows some non-zero scatter in the shape of the IMF. There are other examples. This is a case by Massi et al., a compilation from the Milky Way, LMC, and SMC. You can see again that the line here is the salpeter value, 1.35, and then the clusters are distributed around it, but there is no global overlap within the 1 sigma uncertainty between all the clusters. This is for ensemble of clusters. Now we can look at some individual clusters, and I think the most interesting ones are the most massive clusters, starting from Orion and moving to more massive clusters. If we look at the Orion Nebula clusters, we can see that at the high mass end, it is relatively well described by a power law, but for the very high mass end, we are missing about 30 O stars, high mass B and O stars, and they are not really accounted for in the vicinity of the clusters. So we really don't know if these have been ejected. Maybe a few of them are, but because they are O stars, they would have been easily detected and associated to the clusters. So there is a little bit of a problem here at the high mass, very high mass end of the ONC. Another class of clusters which is showing some deviation from the saltpeter value in the terms of the slope is the so-called starburst clusters. We call them starburst because they have a very high surface density of stars. The surface density is around 10 to the 4 solar masses per parsec square. Compare that to Orion, which is around 100 solar masses per parsec square, which is already more dense than all the low mass clusters. So a perfect example of the starburst clusters is the Arches cluster. Arches is located, I show you here, at towards the center of the Milky Way. So it's at least in projection. We don't know exactly the exact physical distance, but at least in projection, it is only 20 parsec away from the galactic center. And then when people looked at the Arches and measured its slope, and so again, this is there is a lot of work in that regard. Some early work by Stolte and Kim in 2005, 2006. And then, but there is a recent paper by Hosek, this is not Kosek, but Hosek 2020, found that the IMF of this cluster is shallower than saltpeter. The slope, when you fit it by a single power law, is around 1.7 or 1.8. And compare that in this notation to the saltpeter, it's 2.35. So this is shallower than the saltpeter value for the galactic field. If you look a little bit closer, and if you are a little bit picky, you could see that maybe there is even a bump at around 6 solar masses. So there is a slope here between, let's say, 1 solar mass and 5 solar masses or something, which is around 2, and then a shallower slope at above 6.3 with a bump in between, which marks the two regimes. Similar results have been found for NGC 3603, which is one massive cluster, but sitting in the spiral arms of the galaxy. And here the slope is capital gamma is minus 0.87. Compare that to the slope of saltpeter 1.35. So again, this is shallower. It seems that these very massive and dense clusters have a slope that is shallower than the saltpeter value. But again, I would say there is a lot of work in progress on these clusters. We don't have the final answer. There are a number of complications with these clusters. Is that usually people measure the IMF in a certain region of the cluster. The center of the cluster is very hard because there is a lot of crowding, and then you cannot separate the stars. And then in the outer regions, you have a lot of contamination because you are, for example, for the Arches, it's very close to the center of the galaxy, so you have a lot of contamination from the background. So they have been measuring the IMF in a certain ring between, say, one time and a few times the core radius. And so what matters here is proper identification of the cluster members using proper motions, but Gaia has a hard time measuring the proper motions for these clusters because they are much further away. And also you have to account for the dust extinction. For example, if you, so all these things matter. So if you do dust extinction correction, which is general or global, it gives you a different answer from if you do a differential dust extinction correction. How do you account for cluster membership? How do you subtract the background? All these things matter and affect the final shape of the IMF. But the current, let's say, the status now is that these clusters have a slope that is shallower than saltpeter. Priya, do you hear me? Hello?
Yeah, I can hear you.
I just wonder if I should pause if there are any questions before continuing, or shall I go to the end and you tell me.
Actually, I had a question. What is the method you've used for mass determination?
So again, what is the mass?
What method have you used for mass determination?
Which method I have used, or they have? Because I didn't do the observational work myself.
Okay. Actually, I should rephrase my question. Yes. What would you say is the most ideal method for mass determination? Is it isochrone fitting, or should you do SED fitting, or what is the most appropriate according to you?
Well, I think it depends on the age of the cluster, right? If you are looking at very young clusters which have a lot of extinction and especially continue to accrete. I mean, the question if many stars are continuing to accrete, then your isochrone is polluted by these accretion events that are coming on the young stars. So you maybe need to for the younger stellar population, you need to do an SED fitting to see what is the mass of the current protostar. But of course, it will, if you make a model like this, it will give you the mass of the current. You will induce a number from the SED. You will deduce a number of parameters, right? One of them is the mass of the protostar, but you only get the present mass of the protostar. You don't know in 1 million year what it will be.
That's right.
So it comes with that bias. But yes, I agree. If it's very young, you have to. But for the ones that don't have gas anymore, then I think it's HR diagram. But even for the HR diagram determination, now people are using Bayesian inference model. For example, there is a very nice work, and I think the code is public by Fabian Schneider, which is a hierarchical Bayesian inference model from the HR diagram. And he used it on he has a Nature paper on the R136, the 30 Doradus region, in the SMC. And again, 30 Doradus shows that it has a shallower slope because it's a massive cluster. But, I didn't show that cluster here because it's very debated. So 30 Doradus is not like Arches and NGC 3603 because 30 Doradus is very extended. You have massive stars which are a little bit beyond the core area of the cluster. So there is a lot of debate about mass segregation. Have been they formed there? So there is a lot of debate. What is and so it has also very massive stars for which the models are relatively uncertain. Very massive stars, more massive than you have 150 solar mass stars there. So the models are of high mass stars are a little bit inaccurate, possibly. So yeah. So and then the interesting part. So what I wanted to say is that 30 Doradus as a whole is shallow. Similar to these clusters like Arches. But if you look at the central region of 30 Doradus, the R136 cluster, which is just the central part, then it's saltpeter-like. So it is, yeah. So it doesn't mean that it's the mass of the. For me, what that means is it's not the mass of the cluster that matters, but maybe surface density. So how concentrated also the cluster is can play a role. I'm not hearing very well. I don't know if.
Yeah, he can't hear it.
Yeah, essentially the environment should play a big role in the IMF of the cluster, right? The environment is like you've shown that if they're very dense regions, then your IMF has a different slope and so on. So, and even the triggers which have led to the star formation, that should also play a big role. So having expecting a uniform one, I think is really not right.
Yeah. So I will discuss at the end one mechanism by which you flatten the slope in the theoretical part if we get there in time. But so the idea is based on the collision of stars. So you collide stars or protostars, and then you form a shallow IMF at the high mass end.
There's a question in chat. I think.
Okay, let me see the chat because does the initial mass function provides only the initial distribution of masses of stars, or does it predict the future distribution also? Well, the initial mass function is the theories that are about the IMF are about essentially the fragmentation of gas, as we'll see a little bit in the theoretical part. So it's the theories of the fragmentation of the gas. How do you get different a distribution of mass fragments, and how do you move from a core mass function, cores meaning the precursor of stars, so the little gas balls which will give you stars. So so this is from the perspective of star formation. The future distribution relies on other things. It relies on stellar dynamics between stars, and it relies on stellar evolution. It also relies on things like where the cluster is located. For example, if it's located towards the galactic center, or where you have important shear, or if it's affected in general to strong tidal forces, stars can also be stripped from the cluster by these tidal forces. For example, an encounter between a cluster and a massive molecular cloud can also strip stars from the cluster, and then it can take away stars from the cluster. So the future distribution depend on where the cluster is located, so what are the forces acting on it, but also some internal processes of dynamical interaction between the cluster members, particularly between stars and binaries, which lead to the ejection of stars. I think for the second question, the main physical process we will discuss. I will present some ideas in the theoretical part, and so we can discuss this in a few minutes. So I'll move on to the gas-star connection. So I think I provided some controversial discussion about whether the IMF is universal. Does it vary? Does it depend on the environment? So if we want to understand, of course, the origin of the IMF, we have to look at this at the gas. Because this is where stars form from gas condensations within molecular cloud, which are located within the galaxy. So let me first very briefly describe what molecular clouds are. So this is a map in the bottom showing the galaxy seen in the CO. Basically, it's the 12CO10 line, transition line. So this is a view of the Milky Way. You can see a very thin disk with some clouds flying around at a higher galactic latitude. So for the gas to be molecular, it has to be at densities of above a few hundred particles per centimeter cube, typically maybe 600 molecules per centimeter cube, for the molecular gas to be able to start to self-shield. However, what we have is so that's for CO, but the gas becomes molecular. CO is not the dominant component of molecular gas. The dominant component is H2. And H2, molecular hydrogen, and molecular hydrogen starts to self-shield at densities of around 100, maybe 150 particles per centimeter cube, or molecules per centimeter cube. And then so once you reach that densities, the destruction of H2 molecules by UV photons and the recombination rate becomes roughly similar, so the molecular hydrogen can survive. You don't get CO until you reach those densities of several hundreds molecules per centimeter cube, maybe 500, 600. And this is why we speak of also dark molecular gas. It means we can have molecular gas in H2, which is not seen in CO. So what we are seeing here is below is a map of CO, but we can have much more molecular gas, which we don't see in CO. So it can be molecular densities of maybe 200, 300, but it hasn't formed the CO molecules yet, and so we cannot see it. And this is because the H2 molecule is not detectable. You need to heat the H2 molecule to be able to see it at 2000 Kelvin or so. And the CO dark H2 is about half of the mass in molecular gas. So this is important to keep in mind, because half of the mass in molecules is not seen. Actually, we cannot see it that easily. But in numerical simulations, we know that this is how much roughly there is. Now, each of these molecular clouds contain regions which are denser, which are typically 1,000 up to 10,000 particles per centimeter cube, and these are where star clusters can start to form. Within this dense regions, we have even denser spots, which can reach densities of 10 to the 5 or 10 to the 6 particles per centimeter cube. And this is where gravity becomes so important that it's basically overtakes all other support mechanism, and you collapse these dense cores to form individual stars. The molecular gas is generally cold. It's typically 10K. Okay, it can be a little bit higher, maybe 20K, 30K, but typically it's cold. In most cases, it's self-gravitating, means gravity starts to become important, unlike, for example, neutral gas. Molecular clouds are magnetized. We know this now since a while, of course, but we have very nice maps from, let's say, from Planck and from Scuba and so on, from many different instruments. And then, yeah.
So yeah, 5 minutes more, then we'll continue later.
Say again?
5 minutes, and then we'll continue later.
Okay, that's fine, because it's only the beginning of this section, so that's fine.
Yeah. Yeah.
Shall I stop sharing or keep it like this?
We can leave it like this.
Okay, we can leave it like this. Okay.
Or we can just repeat.
We can leave it. I mean, that's fine. In 5 minutes, you said.
Yeah. Yeah. Sami, you can use 5 minutes, and then after 2 hours we are meeting, right?
So are we stopping here now, or?
Yeah, there'll be a break right now, and then you have your second talk after 2 hours, right?
Okay. So did we use already 1 hour?
Yes.
Okay. So you know what? So I had much more material. So what we'll do is then, I think because this is it turned out to be more interactive.
After your second talk, you have extra time because there's a tea break for half an hour, so you can overshoot that time.
Yeah. Okay. So let's do the second talk, the second part of this talk so we meet now in 3 hours, right?
In 2 hours. In 2 hours.
In 2 hours, we meet in 2 hours. Okay.
Yeah.
Yeah.
And then that time you can take a little longer because we have a tea break, so you can use that.
Right? Yes. Okay. We will see how this goes, but that's fine with me. We will meet in 2 hours. Okay. See you then.
Yeah. Is it okay for you to stop now, or you want to continue?
Yeah. No. We can stop now. Actually, the material that is left could fill 1 hour on this talk. So it's actually, I think it's better to do it slowly so that people can take something away rather than rush. I think there is no benefit in rushing anything, right?
Yeah.
We
break for lunch. Yeah. And then the students will come back fresh.
Yeah. Okay. Very good.
And then it's a Friday, so many of them are getting restless to go for prayers, and so they'll come back for that. Okay.
Yes, yes.
So after 2 hours, if you want to overshoot, we have time.
Okay, we will see how this goes. I mean, you tell me. I mean, that's fine with me.
Okay, thank you. That was a lovely talk. And we'll take the questions. Any questions? Okay, so thank you, Sami.
Yeah.
Yeah, we'll continue later.
Yeah.
So all who are joined online, please come back after 2 hours. So it's 1:30 in India. 3:30 we'll reassemble by Indian Standard Time. 2 hours from now. Okay.